Hey guys, it's been a while, but we're going to have a look today at a British Maths Olympiad question, Geometry, 2003/4, question 2. So the question mostly goes, there's a rectangle, ABCD, and P is the midpoint of AB, and there's a point Q on the line CD, such that CQ is perpendicular to PD. I think I put this on the group, but have a go at it first before you have a look. We're going to do two solutions. So today we're going to do like the normal geometry Euclidean solution, which just uses angles and similar triangles, cyclic quadrilaterals. And then tomorrow I'm going to try and show you a solution on vectors, using vectors, which is a different way of proving things in geometry. So this question, we're trying to show that BQC is isosceles. So the first thing I would say is draw good diagrams, because if you don't draw a good diagram, you don't know what you're proving or how you're proving it. So here, showing BQC isosceles, well, you have to know which two lengths you're trying to prove are equal to each other. So once you draw a nice diagram, it becomes clear that the ones that you want to show is that you want to show that BQ equals BC. That's what you want to show, and you can kind of see why it sort of looks like it's true in this case. So you want something about these two angles, ideally. Those are the two angles, X and Y, that you'd really like to somehow figure out if you can. So what we're going to do is look at this 90 degrees, because PD is perpendicular to CQ. So we have this 90 degrees. Now when you see a 90 degrees, look for other 90 degree angles, because you can often find a nice cyclic quadrilateral. And remember, one of the rules for finding cyclic quadrilaterals is that the two opposite angles add up to 180 degrees. So here we have a few different right angles, so I'm just going to draw them all in. Right? We have 4 plus the 1, 5 90 degree angles, but the one that's really nice is these two. That is PBC equals PQC equals 90 degrees. So PBCQ cyclic, because the two angles add up to 180 degrees. So if they're cyclic, we have a few other quite nice things that come about as a result of it. But what I'm first going to do before I look too much into that cyclicity, I'm also going to draw this line here. Now, we've used this 90 degree angle, but we haven't really used this midpoint, right? So these two, this is a midpoint. P is a midpoint of AB, which means that AP and PB are equal to each other. So AP equals PB, and we also have that AD equals BD. Why? Because it's a rectangle. And finally, we also nicely have that PD. So we have that let's write it one more time. PAD angle equals PBD equals 90 degrees. So those two triangles are just a reflection of each other, and by these three rules we have SAS congruency. Right? And so this means that this angle here, which we're going to call theta, right? And this angle here, which we know is 90 minus theta, because this angle is 90 degrees. And this angle here is also equal to theta because of the two similar triangles. Nice, right? And we also have that because of this cyclic triangle, quadrilateral, that this here is also theta. Right? Starting to get quite a few thetas, right? So this is theta. Now this one here is 90 minus theta. Remember, this is also 90 degrees. So this is theta. Wow, great. So this angle here is 90 minus theta. And then now if I just remove this one again, because that's theta, we again have that this is 90 minus theta. So voila, now we have that this triangle is isosceles because the two angles are equal, which means that BQ equals BC. Right, so all we did was we noticed a similar triangle, SAS congruency, and we had this cyclic quadrilateral. Then we just followed the angles around and it worked really nicely. So great. I'll see you guys tomorrow for the other solution. Bye.